Let's talk about the four fundamental forces, and one of them is responsible for this. Let's start by talking about the fundamental force that I think is the easiest to understand and is the reason behind why I dropped an apple at the beginning of this video. Besides the fact that it had been sitting in my backpack for a while, the falling apple is a perfect representation of gravity. It's a common legend that Isaac Newton was sitting under an apple tree when all of a sudden an apple fell, hit him on the head, and that's what got him interested in studying gravity. According to scholars, there isn't actually evidence that an apple actually hit him on the head, though in his family's orchard he likely witnessed apples falling from trees, and that really sparked his interest in studying gravity. One of Newton's most important contributions has to be Newton's law of universal gravitation. This law in equation form is F force equals gravitational constant times mass 1 times mass 2 all over the distance squared between those objects. Now you might ask yourself, what exactly does this equation mean? If we look at it, we see that as we change mass, the force will increase or decrease linearly, whereas if we change the distance between those objects, force will increase or decrease exponentially. If we look at a situation where we have four of the same mass, though I've labeled them as mass 1 and mass 2, and two of them are at a distance of 2 meters, while the bottom two are at a distance of 1 meter, we can use our equation, and since the gravitational constant, mass, all that on top is going to be the same in each case, I just put a 1 on top. We can see that since you're at a distance of 2 meters, our relative force felt would be 1/4, whereas at a distance of 1 meter, the relative force would be 1. Decreasing distance between two objects increases the force of gravity. While gravity is often thought of as a really strong force, it is actually the weakest of the four fundamental forces with a relative force of 10 to the negative 38 power. Now let's think, what should be the name that we give to a force that's stronger than gravity? I know, the weak force. To be completely honest, the weak force is completely weird and gets extremely complicated extremely fast. But I think understanding some of the key elements of the weak force can help us appreciate it and better understand this important force of nature. While the weak force is much stronger than gravity, it actually has a relative value of 10 to the negative 13, whereas gravity was 10 to the negative 38. The weak force only occurs at very tiny distances. Nearly everyone knows the basic structure of an atom, right? You have protons, neutrons, electrons. But the thing we often forget is that protons and neutrons themselves are made of smaller fundamental particles called quarks. And whoever named them quarks, I don't know why. Regardless of the strange name, both neutrons and protons are made of 3 quarks each. This, believe it or not, is a proton. It consists of 2 up quarks, which just defines the state that the quarks are in, and 1 down quark. Up quarks have a slight positive charge and down quarks have a slight negative charge, which would make sense since protons are overall positive. Neutrons, on the other hand, have 2 down quarks and 1 up quark. The orientation of the quarks fundamentally describes whether something is a proton or a neutron. And if you could change the states of those quarks from up to down or down to up, you can change that proton or neutron. Let me show you what I mean. To be clear, the manifestation of the weak force is the changing of the state of the quark from up to down or down to up. Let's say that you have a down as part of a neutron, so 2 down and 1 up, and you have a fundamental particle called a neutrino approach one of the down quarks. When it comes to the weak force, there are 3 primary force particles that can act in this situation and even change quark orientation. They are the W boson, which can be positive or negative, and the Z boson, which is neutral. In this situation, if this neutrino transferred a W positive boson to this down quark, the down quark will turn into an up quark, and then overall you have 2 up quarks, 1 down, so you get a positive proton. How's this even relevant to physics? Well, the weak force is responsible for radioactive decay, which is critical to understand because we use things like carbon dating and even nuclear power, a whole host of things that require knowledge of radioactive decay, which bases itself around the weak force. What then, you may ask, is the next strongest force? It's one that can be a little confusing, but it's called the electromagnetic force. For the longest time, electricity and magnetism were thought to be 2 separate forces, though in 1837, a guy named Maxwell published something called A Treatise on Electricity and Magnetism. In his work, he published 4 equations that really help tie electricity and magnetism together. Maxwell's first equation helps us realize that electric field lines start on a positive side and end at a negative side. And this is a basic representation of the fact that electric field lines go from positive to negative. Maxwell's second equation describes magnetic field lines and that they are continuous. Unlike electric field lines, they go on forever in a never-ending loop. It's important to realize that the source of all magnetism is current, and that if you cut a magnet in half, you'd get 2 new magnets. You can't have a magnet without 2 poles. Maxwell's third equation describes the fact that a moving magnetic field, like we have in this scenario, with the magnet moving up through a coil, this movement will create an electromotive force or current. Though if this magnet were to just stay still, that current would go to 0. It should also be noted that per Lenz's law, the induced EMF opposes the change that that magnetic field is undergoing. The last of Maxwell's equations, and related to the third equation, is the fourth, which says that magnetic fields can also be created by moving charge. As an example, if you had current moving in this upward direction, then there would be a magnetic field created loopwise around that moving electric charge. Electromagnetism, compared to the other forces, is 10 to the -2, and it comes in as the third strongest fundamental force. The last force we have, the strong force. Look, I'm not that strong, but the strong force is the strongest of the 4 fundamental forces, and subsequently has a relative value of 1. One cool thing about the strong force is it's kind of like a Goldilocks force, where it can be strongly repulsive at really short distances, though at a slightly larger distance, it is extremely attractive. So it keeps particles in a perfect range that's not too far and not too close together. When we talked about quarks in the weak force, I left something out because I didn't want it to get too confusing. But let's get confusing. In addition to the orientation of the quarks, each quark has a color. And no, I'm not talking about a real physical color. It's just another state that the quark is in. And those include red, blue, and green. Now, some ground rules: you can't have more than one of the same colored quark in a proton or neutron. Each one of these will either be red, blue, or green, and that we will have all 3 colors represented in this proton. Part of the strong force is that the color of each of these quarks is constantly changing through the strong force via something called a gluon, which is a really good name since the gluon helps keep this proton together. The colors between all 3 are consistently changing back and forth, and this action helps keep this proton together. You've probably tried this, but if you stuck 2 positive ends of a magnet together, they violently repel, and you basically can only hold them together if your hand is physically holding those magnets together. If we were to look inside an atom, we would see a lot of protons together, which are highly positive and you would think highly repulsive, right? Probably the best way to understand how protons and even neutrons, all that is able to stay within the atomic nucleus is that through gluons, there's able to be color shift between different protons and neutrons. neutrons, and that interaction keeps everything tight and close within the nucleus. So there you have it, a basic overview of the 4 fundamental forces that we see in nature. This isn't the apple I dropped.